Hello and welcome to this little video. I just got done teaching intrusion detection, our SEC 503 class yesterday. So I'm still a little bit in a packet mood, kind of, talking about packets for a week and diving into them. So figured today I just take a look at some of the alerts I'm seeing here in my home network and maybe show you how to dig into them a little bit and discover some new and interesting stuff. So let's take a look here and do a quick tail here on my Suricata logs. So Suricata, actually, let me first show you that. Creates a number of different logs. Statistics here about Suricata, these events, they're always very interesting, but we sort of want to use it today sort of as a classic intrusion detection system, and I'm just looking at the fast log, which is very similar to what you would get with Snort. So let's just look at the last few here and see what we have here. And let's see, there are some Oracle SQL port, not really that terribly interesting. These are usually just some, block-listed IP address that is hitting you. Actually, these DNS amplifications, haven't looked at them in a while. Let's take a look. Let's see what we got here. What you typically see here is some kind of inbound request for an any record for a domain that then attempts to trigger some kind of amplification. This source IP address is often the victim of the denial of service attack because they would be receiving the amplified results. On the other hand, of course, attackers sometimes will just scan the internet for possible amplifiers. Doubt that is the case here because we see a lot of incoming requests here from the same IP address. So this may already be an attempt to amplify. As far as I know, I'm not amplifying, so let's verify this, and let's take a quick look what's going on here. So let me just copy that IP address, and let's look at it in more detail. Now, in Suricata, you have the ability to also capture packets. That's not what I'm doing here. I have a separate system that just captures packets from the network, regardless of whether they're malicious or not. So let me switch to this. I'm using Archime. If you're not familiar with the tool, great tool. It used to be known as Moloch. And it's basically a tool that collects all packets from your network and then indexes them in Elasticsearch database to make them easily searchable. So let's see what we have here for this IP address. Let's see what we got. Okay, yeah, we got a bunch of DNS requests here. You see this nlrb.gov is sort of one. There are actually a couple of .gov domains that make real great amplifiers, sadly. But looks like we're not responding. I only see the requests coming in. I don't see responses going out, which is good. Okay, let's just get some of these packets. Let me get a little bit more data here. So here's by default as the last hour. Let's get the last 24 hours. And you actually now see at the graph up here how we sort of get a continuous stream of these packets coming in. There doesn't really seem to be sort of any periodicity to it or as such. It just sort of keeps coming in. And then in Archime, we can now easily get the full packets that match here. And actually, let me do this a little bit different. Maybe in case there are other IP addresses, let me not just filter by the IP address. And here you see the status code was refused. But let's just filter all the any requests, because that's usually the query being used in these denial of service attacks. The any record, it's sort of a wildcard. It returns anything known about that domain, which of course can be a lot of data. Okay, so let's just actually do just the DNS query type any and do a search. It looks a little bit different. It looks like there's some other traffic here as well. So great, and we have a little bit more. We actually also have some any traffic to port 5353. This is like the local network discovery. We don't want that. This multicast DNS. Let's just make sure that we also limit it to port 53. Okay, and now we sort of got something more resembling what we had earlier in the graph up here. And then let's export the PCAP. So here I'm saving this now. The file name here was session1. I'm doing this ever so often, so that's probably why you see the other session files here. Didn't delete the old ones yet. Okay, so let's go back here to Suricata, actually to the terminal, and to my downloads. Let's just do a quick TCP dump on the sessions 1 PCAP. Okay, just quick look here, see if what we get makes sense. Yeah, and here we have sort of these. Okay, there's also like an ncaa.mil. Let's actually see what that record is. So let's do a quick any lookup, ncca.mil, just to see what we get back here. And yeah, you see that's actually almost ideal for amplification here, this record, in that it gets 4,000 bytes back, creates sort of with DNS 0 and such, may get some nice fragmented UDP packet stream. So you see one part of the reason here is that this uses DNSSEC. So you have all these digital signatures being included here. And often there are also some text records and such, like for domain authentication. I don't actually see this here, just a DNS key. There is actually a recent RFC to prevent some of this. And let me just, like one record I've often seen is like x.com. And see here that they basically have a very minimum response. And if I go directly to one of their name servers, yeah, then I get a full response back. But where name servers are sort of only returning the minimum required, not the full response, and even some outright block these any requests now. And there's a newer RFC that does actually suggest that and essentially allows you to block replies to any requests, so you don't have to respond to them. They're on the public internet. There's really not that much use for these any queries. But anyway, so let's take a little bit more look at our PCAP. So it was our PCAP here, and let's just use T-Shark so we get a little bit more detail. And get the verbose version here. Actually, let me go one step back here and see what source IP address. Yeah, actually, T-Shark. Sorry, T-Shark. So sessions 1 PCAP, and then let me just extract the source IP addresses. That's always easy to do in T-Shark. Could do it in TCP dump, but the file is short enough. It's kind of easier to do it here in T-Shark. Where we just have extract the source IP here. Let's see if I got this right. Yep, and here we have the IP addresses. So let's do a sort -u. Actually, let's just do a sort and then a unique -c, so we get all the unique ones and count how often they show up. And yeah, here that 45 one is our top one. The 70 and the 10, these are my internal IP addresses here. This one looks like another one that is playing similar tricks here. So let's just take a look at everything coming from this IP address. Let's go back here for TCP dump, just because it has typically a little bit more compact output. I'm using the verbose mode here, so you get a little bit more detail about the DNS queries. And then just host. And let me just make the source host here, make it cleaner. And let's turn off the timestamp, because probably don't need it here either. So anyway, yeah, here we have some of these records. We see a lot of these ncaa.mil records here. nlrb.gov is another one that they're liking. Oh, now we have some interesting stuff happening here. Some odd domain names here. Let's actually look at this a little bit in more detail and see what we get here. Also notice they're using eDNS 0 to its fullest extent. eDNS 0 allows you to specify that you're willing to accept larger UDP response. And you noticed earlier that the response was something like, in excess of like 4 kilobytes. So here it actually tells the server, hey, just send it all back as UDP. And that's, of course, ideal for a denial of service because now it may get fragmented. It makes it much more difficult for the victim to handle all of these replies coming back. But yeah, I want to take a little bit of a look at this something c.co and see what this is all about. And looks like the first record here's one, so that makes it kind of easy to filter it out. Just the first record, yep. And then let's write that to that DNS.pcap. Okay. And actually, let's do a T-shark quickly on it and get all the details here from T-shark to see what we get for this one. Okay, so let's take a look. So it tells you it's a standard query. The query flag is cleared. The recursion desired flag is set. That means whichever DNS server is receiving that, even if they're not authoritative, they're supposed to go out and find the answer. That's exactly the problem with these amplifiers, that these are DNS servers that will do recursive queries for anybody. So that's what they're exploiting here. We do have one question, and we do have one additional record. And yeah, that's the question. So a little bit an odd name here. Name length 4. We have one label. Okay, there's it's basically technically sort of a top level domain here that we are looking for. And then here type any, that's what we're expecting. Class internet, it's always class internet. And then we have one additional record, and that's our extended DNS option 0. So here we basically specify that we do have that long payload length here. So that's pretty much what we got here. But let's look a little bit at the query here. And to do this, let me just switch back to TCP dump. And turn on capital X so we see the hexadecimal output here. And do I need anything else? I don't think so. And I'll leave this up here so we can sort of switch forth and back a little bit. And let's sort of do a proper packet walkthrough here. We have IP version 4. We have an IP header length of 5 times 4, so 20 bytes. Type of service of 0. We have a total datagram length of 3 delta. So that's 53, I think. And then we have IP ID, some random IP ID here. Do not fragment flag is set. No fragmentation happening here. And next, we have our time to live, F2. It's pretty large. Usually it's like, 128 or lower, or 64 and lower. This looks like it started at FF at 255, and then we sort of lost a couple hops here until it reached our network. Our protocol is UDP 17. Then we have our checksum. Then we have our IP address. That's the source IP. So here 45, 148, 10, 248. And then we have our destination IP 7091 1459. Okay, so this is our IP header. Nothing remarkable about this, just a perfectly normal IP header. Well, I guess you can sort of consider that somewhat high TTL as remarkable. Okay, then we have our source port. Apparently this is 18177. Our destination port, of course, 53. our UDP length, 29, that's 33 bytes here. And then we have our UDP checksum. An empty UDP checksum is actually kind of, it's not normal, but it's allowed. So usually a checksum of 0 can never happen. It would automatically mean, hey, this is a bad malformed packet. But in UDP, there's a special case in IPv4 where the UDP checksum is optional, and a checksum of 0 just means, hey, don't bother checking it. And in particular for the denial of service tool that is trying to send packets as fast as possible, not wasting cycles on calculating checksums, kind of makes sense. Okay, and then we have our query ID. So if you go back up here, the query ID here, we have it here, 4567. And then we have our flags, where the only flag set is this recursion desired flag. Next, we have the number of queries, 1. Then the number of answers, the number of authority records, and then the number of additional records. And the additional records here are this option we saw earlier. And this is normal for a query, that you have one query and then some additional record. So with the option, and again, this option is normal. What's not normal here is the large UDP payload size. Typically, that's 4 kilobytes. That's of the most common one I see. Sometimes I see 1 kilobyte being advertised here. 1 kilobyte, of course, to avoid fragmentation issues. But 4 kilobytes of by far the most common UDP payload size here that is being seen. Okay, so next we start with our records. The record now is of that length label. So we have a length of 4, and then we have, well, the next 4 bytes here would be our label. Now, the odd thing here is that 03. That 03 is not quite right here. So that's where things are a little bit tricky. I think what may have happened here is that they didn't construct these host names correctly. Because if you look at it, now we have here O and CO. CO is a commonly used, Columbia, often used as a domain name, sort of also to sometimes simulate like .com. If you don't get the .com, you sometimes get the .co name. So if this would be 1 here, then 6 Foxtrot here, O, and then this should be 2, and then we have 636F, and then we have here the 0 closing it out. So that would all make sense. So probably a broken denial of service tool. Hope they're not listening, and hope they are continuing to send bad traffic that's really just not going to work. But we also saw some valid queries from them, so looks like, they don't always get it wrong. Yeah, and then we have our any record here, that's the FF, the internet zone, and then we have here our options, option type 0, and then we have here that 29FF. That's here the actually it's not the payload size is back here. Sorry, it's 29. That's the option type. And then we have FFFF. That's our UDP payload size here that we have. And then a couple zeros here at the end. You see here for various other sort of flags and such related to the to this option. But anyway, so that's it. Looks like these people are, first of all, using some .gov domains to do denial of service attacks. And yeah, it's sad. There are a bunch of these domains out there. Let's actually try to extract them quickly. So DNS query name should give us what they're looking for here. And let me get the entire file here. Okay, and then let's just do a sort-u, yeah. So there's this ncca.mil, nlrb.gov, and then this malformed one. And this SL looks like another possibly malformed one that is being used here, but we don't see one of the odd characters, so that may be something else they're trying to do. But again, if you're doing like a quick dick any, let me try the nlrb.gov to see what's coming back here. Actually, this one is really small. Yeah, and actually here, looks like they fixed it. When you see this RFC 8482, that's the RFC basically allowing you to not respond to these any requests. And for some name servers, you see then this host info record instead of the full set of records being returned. If this RFC is implemented, let me just tell you, okay, no, we don't return anything here because of this RFC allows us to do so. Sometimes you see them outright blocked or not being responded to. That's, of course, another valid option to deal with these any record requests. So anyway, that's all I have here. Hope you like it. If you like more like this, remember, a year or so ago, I did like this Packet Tuesday where I had a bunch of videos where sort of us diving into packets. Probably leave a link somewhere wherever I'll be posting this shortly. So thank you.